Welcome, my dear learners, for this course on tribology. So far, we have solved 3 numerical problems on idealized full journal bearing. Let us continue from the point where we have stopped in our previous lecture. Let us solve problem number 4 of our discussion on idealized full journal bearing in today's lecture. The problem number 4 states that automobile oil SAE20 is used to lubricate a hydrodynamic journal bearing of diameter 75 mm and length 75 mm. The journal rotates at 1200 rpm. The diametral clearance is 75 micron meters. Assuming operating temperature of oil as 53 degrees Celsius, determine magnitude and location of minimum film thickness, eccentricity and eccentricity ratio, oil flow through the bearing with and without side leakage. Also find side leakage. Let us address this problem. This problem is based on side leakage. Now, if I list out the data given for problem number 4, we have automobile SAE20 oil, which is used to lubricate hydrodynamic full journal bearing. So, we have automobile SAE20 oil. We have automobile oil SAE20. The bearing diameter is specified, that is 75 mm, which is equal to length. The journal rotates is specified in rpm, therefore it is capital N. Then N dash is rpm by 60, that is 1200 by 60, which is nothing but 20 rps. The diametral clearance, capital C, is 75 micron meter, which is nothing but 75 into 10 to the power of minus 3 millimeter. So micron meter refers to 10 to the power of minus 6 meters. I am taking 10 power minus 3, and remaining 10 power minus 3 meters can be written as millimeter. Assuming the operating temperature, we specified the operating temperature given as 53 degrees Celsius. He is asking us to calculate the magnitude and location of the minimum film thickness to find H minimum and phi, eccentricity and eccentricity ratio, that is attitude, epsilon, oil flow with and without side leakage, and oil flow in side leakage. How much is the side leakage? So this is what we should compute. Now, since he has specified the oil, that is SAE20 automobile oil, and the operating temperature is also known for us, that is 53 degrees Celsius. So therefore, let us directly determine what is the viscosity by using table 24.1 and figure 24.2a. Whenever the operating temperature is not specified, always assume the operating temperature as 60 degrees Celsius and solve the problem. Now, if I look at table 24.1, if I look at table 24.1, automobile oil SAE20 automobile oil SAE20 is belonging to type E. Now, using the type, determine the viscosity by using figure 24.2a. So using figure 24.2a, referring to page 24.6, referring to page 24.6, at 53 degrees Celsius operating temperature, for type E, So from the graph, if I look at the graph, we have graph like this. The graph is like this. We have operating temperature TO, we have oil type is E, we have eta in centipoise. Eta is specified in y-axis in centipoise, whereas x-axis contains the operating temperature. At 53 degrees Celsius, if I intersect this and come horizontally, I can find that Cp is found to be 32 centipoise. We have the operating temperature as 53 degrees Celsius specified for us. So at 53 degrees Celsius, intersecting type E curve and plotting it horizontally to y-axis, I found that eta is found to be, absolute viscosity is 32 centipoise, which is nothing but 32 into 10 to the power of minus 3 Pascal second. 32 into 10 to the power of minus 3 Pascal second. So we have calculated the absolute viscosity. Now we know RPS, that is 20 RPS, and also we know the value of diametral clearance. So since diametral clearance is known and diameter is also specified, I can determine diametral clearance ratio. Now diametral clearance ratio xi is given by diametral clearance by diameter, right? How much is diametral clearance? Diametral clearance is 75 into 10 to the power of minus 3 millimeters. Diameter is 75 mm, hence diametral clearance ratio will be 10 power minus 3, that is 0.001 is the diametral clearance ratio. Since he has specified side leakage, we cannot use figure 24.12. Whenever the side leakage is specified, we should go for figure 24.24 to find the value of flow variable delta, using which I can find the value of minimum oil film thickness. Usually we will be using figure 24.12 to determine film thickness variable delta, using which we can find minimum film thickness if there is no side leakage. If side leakage is specified, we should refer figure 24.24. Note, figure 24.12 is used for no side leakage. But in our case, he has specified the side leakage and is asking to calculate how much is the side leakage. So therefore we cannot use figure 24.12 to find Sommerfeld number or to find delta, that is film thickness variable. As he is specifying the side leakage, I can determine the leakage correction factor. Therefore from figure 24.24, from figure 24.24 we have load correction factor for side leakage, which is like this, which is plotted against B by L versus we have the curve. Now the value of B by L, that is B, which is equal to pi d into beta by 360 degree. This is given in equation 24.19. For full journal bearing, beta is 30 degrees, 360 degrees. For full journal bearing, beta, value of beta is 360 degree. Therefore, the value of B is pi d into 360 by 360. It is pi d. Hence, B by L is pi d by L. For us, yes, specified diameter is equal to length. So therefore, since diameter is equal to length, I'll get the value of B by L as 3.141, the value of pi. So this is load correction factor due to side leakage. If I intersect at 3.141 and plot it horizontally, I'll get flow correction factor as, here we have correction factor, values of correction factor, where I am considering load correction factor due to side leakage because he has specified the side leakage. At 3.14, if I intersect and plot, I'll get the value of load correction factor due to side leakage as 0.085. Next, moving ahead, by knowing the value of load correction factor due to side leakage and the value of B by L ratio, which is equal to pi, I can find what is the minimum film thickness variable, that is from figure 24.26. From figure 24.26, we can find the minimum film thickness variable delta. Film thickness variable delta can be found to be 0.8. So referring to figure 24.26, for load correction factor CW, which is equal to 0.085, and B by L ratio, which is equal to 3.141, I found that flow variable delta is equal to 0.8. So once I calculate the value of flow variable delta, I can easily compute what is the value of minimum film thickness, because we know that delta is equal to 2H minimum by C. This is equation number 24.33, which is also equal to 1 minus epsilon. This is equation 24.33, page number 24.14. Page number 24.14. The value of delta is found to be 0.8, which is equal to 2 times minimum film thickness by C. The diametral clearance is 75 into 10 to the power of minus 3 millimeters. Hence, minimum oil film thickness will be 0.8 into 75 into 10 to the power of minus 3 divided by 2, which is equal to 0.03 millimeters. Now I can find what is the value of eccentricity ratio, epsilon, that is delta is equal to 1 minus epsilon. Hence epsilon is 0.2, because flow variable delta is 0.8, 1 minus 0.8 is 0.2. Now I should find what is the value of minimum film thickness and eccentricity E. So to find eccentricity E, I can use the value of epsilon, because now epsilon is given by 2 times eccentricity by C. This is equation 24.30. From equation 24.30, we have the relationship between eccentricity ratio and eccentricity. So I'll get the value of eccentricity as 7.5 into 10 to the power of minus 3 millimeters. it is 0.2 times C is 75 into 10 to the power of minus 3 divided by 2, which is nothing but 7.5 into 10 to the power of minus 3 millimeters. Now to find minimum film thickness, as usual we can refer figure 24.11a. Figure 24.11a of page number 24.30 gives us the location of minimum film thickness. But this minimum film thickness is a function of Sommerfeld number. Now Sommerfeld number is usually determined by using the value of delta from graph 24.12. But figure 24.12 cannot be used because this graph is for no side leakage, but the problem what we are encountering is based on side leakage. So therefore I should go for figure, use figure 24.13a, use figure 24.13a referring to page 24.33. 24.33, this is with side leakage. Now we have the value of delta. Delta is 0.8 and the value of L by D ratio is known. L by D ratio is 1. So from this graph we have Sommerfeld number versus L by D ratio curve, and here we have the value of flow variable delta. Now intersect at 0.8 for L by D ratio is equal to 1 and plot it vertically downwards, you get the value of Sommerfeld number, and the value of Sommerfeld number is found to be 0.65. 0.65 is the Sommerfeld number. Now using Sommerfeld number, using our regular graph that is 24.11a to find position of minimum film thickness, I have found out the position as 75 degrees, that is from figure 24.11a referring to page 24.30 for the value of Sommerfeld number is equal to 0.65 and the ratio of L by D is equal to unity. We have position of minimum oil film thickness as 75 degrees. Now moving ahead to find oil flow through the bearing. That is, to find the oil flow through bearing, I should refer graph. Now to find oil flow through bearing, refer figure 24.37. Refer figure 24.37 of page 24.35. Using the value of Sommerfeld number, S is equal to 0.65 and the value of L by D ratio, which is equal to 1, we can find what is the value of flow variable lambda q. So this graph is like this. We have flow variable versus S versus flow variable lambda q, and we have curve for L by D ratio. So at Sommerfeld number is equal to 0.65, move up, intersect L by D ratio is 1 and come horizontally and plot, note on the value of lambda q. So I found the value of lambda q as 3.6. Now from the frame figure, in the y-axis he has given formula for lambda q lambda q is given by 4 times flow rate into xi divided by c square n dash l. So therefore I can find the value of q without side leakage. Q without side leakage will become lambda q into c square into n dash into l divided by 4 xi. If I substitute all the values and solve, I'll get the answer as 7.593. 7.593 into 10 to the power of minus 6 meter cube per second. Into 10 to the power of minus 6 meter cubes per second. Now to find flow rate with leakage, with side leakage, refer figure 24.38, which gives us the ratio of flow with side leakage to without side leakage, that is for delta is equal to 0.8 and b by l is equal to pi. We have the value of ratio of flow with leakage to without leakage, which is found to be 1.3. Now the definition of CQ is that Q with side leakage is equal to Q without side leakage into CQ. Hence with side leakage is 1.3 times this one. So without side leakage multiplied by 1.3 will yields us the value as 9.87 into 10 to the power of minus 6 meter cube per second. So this is the value of oil flow through the bearing without side leakage and with side leakage. Now moving for the amount of side leakage, the final point. Now to find the amount of side leakage, I have to find the ratio of side leakage to oil flow rate. That is from figure 24.39. From figure 24.39 for Sommerfeld number is equal to 0.65 and L by D ratio is equal to 1. We have the ratio of side leakage to flow rate, which is obtained as 0.26, which I obtained as 0.26. So therefore side leakage is 26% of overall flow Q. So therefore 26% of flow with side leakage will yields us a value as 2.57 into 10 to the power of minus 6. 2.57 10 to the power of minus 6 meter cube per second. So this is the complete solution for problem number 4, wherein which we have solved a problem on idealized full journal bearing with side leakage, for which I calculated the value of magnitude of minimum film thickness, position of minimum film thickness, side leakage, oil flow rate with and without side leakage, and also we have computed eccentricity and eccentricity ratio. Always remember, whenever we want to find the position of minimum film thickness or Sommerfeld number or minimum film thickness, we always make use of graph 24.12 This graph should be used if and only if there is no side leakage. Whenever the side leakage is specified, to find Sommerfeld number, I should always go for figure 24.13a. So 24.12 is without side leakage, whereas 24.13a is with side leakage. So this is the complete solution for problem number 4. That's all from this lecture. Thank you all.